Hi, welcome to Send to Print. Sometimes the hardest part of designing a 3D printed model isn't the part itself, but figuring out how to connect two parts together. Screws work, glue works, and snap fit joints work too, but each one comes with its own trade offs. Today, we're making a dovetail joint, which is great when you need two parts to hold together under tension. The basic version works, but I made a few upgrades to make it cleaner, stronger, and easier to assemble. Let's jump right in. First, let me explain how a dovetail joint works. It's a traditional woodworking joint. One part has an angled tail, and the other has a matching socket. To assemble it, the tail slides into the socket from one direction. But once it's seated, you can't pull it straight out because the angled faces lock against each other. The harder you pull, the more those faces press together. That's what makes it so good under tension. All right, let's get started. I started with a simple cube. On one edge, I sketched the dovetail profile. It's basically a trapezoid. To keep it centered, I used a midpoint constraint between the dovetail and the cube. Then I locked down the profile with a few fixed dimensions. Traditional woodworking dovetails are usually cut at around 7 to 14 degrees. That range depends on things like wood grain, how strong the thin tips are, and what tools you're using. But we are 3D printing this, not cutting it from wood, so the rules change a bit. We don't have to worry about wood grain splitting, but overhangs, print orientation, nozzle width, and friction still matter. If I measure this one, it is 26.6 degrees. That would be weird for woodworking, but for a 3D printed part, it's totally fine. Next, I extruded the dovetail and merged it into the cube. That gives us the tail side. Then I created the matching part, the green socket side. I used the combine tool to cut the matching socket using the tail. And now the socket side is ready too. Let's take another look with the section analysis. It looks like a perfect match, but that is exactly the problem. If we print it as is, the two parts will be too tight to slide together. We need a little clearance here, just enough for the two parts to slide together. Okay, let's send them to print. I made two clearance versions, 0.1 and 0.05 millimeters. This is the 0.1 version. It slides in almost effortlessly. The dovetail locks really well against pulling, but in the sliding direction, it's way too loose. If I pick it up like this, the parts can just slide apart. Here's the tighter one with 0.05 millimeters of clearance. Let's put it together. This already feels much tighter. It takes some pressure to push in. Still locked against pulling. And it does not fall apart when I lift it. A tighter clearance means more friction, so the joint is harder to slide back out. But this number is not universal. It changes with the printer, material, and even the direction you print the parts. So now the dovetail works, but just working isn't enough. We want it to feel smoother, hold better, and look cleaner. Let's start with the most obvious fix, the edges. I added fillets to both the tail and the socket, and here's a little trick. I use different fillet sizes on the inside and outside corners, so those sharp areas have a little more space and do not scrape against each other. On inside corners like these, I used a 0.3 millimeter fillet, and on the outside corners, I used 1.5. That gives the corners a bit more room to move. Now, let's try the fillet version. First, the one with 0.1 millimeter clearance. It slides in easily. Still too easily, honestly. Now, the 0.05 millimeter version. It is a little tight, but with a bit of pressure, it seats properly. And it still holds well when I pull on it. The rounded edges make assembly smoother, and you'll notice it more with the tighter clearance. On the sharp version, I really have to force it in. You can hear that rough, scratchy sound. The rounded version goes in with less effort and without that harsh scraping sound. The reason is simple. Sharp edges love to catch. A small rounded edge gets rid of that annoying scrape. But honestly, the assembly still does not feel quite right. 0.1 clearance is too loose. 0.05 is too tight. Sure, I could set the clearance in the middle and keep guessing, but there has to be a better way to design this. Ideally, we want an easy entry with a firm fit once it's fully seated. So I changed one small setting in the dovetail extrusion, the taper angle. Here I set it to 0.3 degrees. That means the dovetail slowly gets wider along the sliding direction. So the entry end is smaller and starts easily. As it slides in deeper, the fit gets tighter only near the end. Okay, let's measure it. This lower edge is 10 millimeters. The top edge is 10.5, so it is 5 millimeters wider. You may have noticed I used 0.3 degrees here, but don't just copy it for every project. I find it easier to think an actual size difference. So instead of using a fixed taper angle, I adjust it until the larger end is about 0.5 millimeters wider than the smaller end. All right, let's make the matching socket the same way as before and print the test parts. Here is the tapered version. At first glance, it barely looks different because the taper is so tiny. But if you look closer, the lower edge on the right is just a little shorter. Okay, let's start with the 0.1 clearance version. The first part slides in easily, and only the last section needs a little push. And it still holds when I pull on it. To disassemble it, I need a small push at the beginning, then it slides out freely. So you can see, with the same 0.1 millimeter clearance, the straight version can slide apart, but the tapered one does not. Now let's try the smaller clearance prints. This one gets tighter near the end too, but only over the last 5 to 10 millimeters. Fully seated. Overall, this feels much better. Most of the movement is easy, and the resistance only shows up at the very end, so I don't have to force it the whole way or listen to that scraping sound the whole time. And it performs better with different clearance values too. The fit feels good now, but the joint is still very visible. Can we hide it? So I went back to Fusion and changed it into a stopped dovetail. The dovetail still does the mechanical work inside the part, but the outside face stays clean. Let me quickly show you how it works. This is the tail side, and this is the socket side. First, the tail drops into this full-size opening. This part is not the dovetail slot. It is more like an entry pocket, big enough for the tail to go straight in. From there, it slides down into the real dovetail slot. Thanks to the stops at both ends, the dovetail is now completely invisible from the outside. But now, this part of the dovetail would be printed in midair instead of sitting on the build plate. So I added a chamfer underneath, making it 45 degrees so it can print cleanly without support. Here is the printed hidden dovetail version. It drops in first, then slides down. Let's see if it works. Okay, it is fully seated now. The dovetail is hidden all the way around, and it still holds against pulling. With tighter clearance, it also takes some real force to slide back out. To make it easier to line up the tail with that full-size opening, I added a lead-in chamfer. It gives the part a small ramp to follow, so it can find the opening without perfect alignment. Here it is. That lead-in makes the slot much easier to find, almost like a tiny funnel. Now let's look at the bigger problem. The trade-off is that hiding the dovetail makes the joint shorter. Originally, this was the load-bearing length, but in this hidden version, the effective engagement length is much shorter, which means less contact area. While the joint still works, the same load is concentrated on less plastic, reducing both its tensile strength and the friction needed to keep it seated. With a straight split, you can see I only get this much engagement. So instead of making the part bigger, I changed the split line. With the same overall size, an angled split gives the dovetail a longer path through the part. More length means more contact area, so the load is spread out better, and the joint gets stronger. The one on the right is the angled split version. The tail is much longer now, so with the same pulling force, the stress is spread across more material. The assembly is basically the same, just on an angled split. It drops in, then slides down. Let's try it. And now the joint is hidden, but the dovetail has a longer, stronger engagement area inside. All right, that is the final dovetail joint. Rounded edges to reduce sharp corner friction and that scratchy sound, a small taper for easier assembly, a stopped dovetail to hide the joint, a lead-in chamfer to make alignment easier, and an angled split to bring some strength back. I've uploaded 2 versions of the test joint to MakerWorld so you can print them and test the fit if you are interested. And as usual, channel members get early access to this video, plus a cheat sheet with the key design principles, and a behind-the-scenes Fusion file. Okay, that's all for today. If you found this tutorial helpful, please hit the like button and subscribe for more 3D printing designs. Let me know in the comments what should I model next. Thanks for watching, and I'll see you in the next one.